Now we're going for the fourth. It was transformation. Yeah, this one is very interesting. Transformation with Kangaroo 2. Somehow it always create error message for me. This one, it requires another plugin. How does that call? I don't quite remember. The plugin is from the same author as NGon. And I think that plugin is also very interesting and very useful. Oh yeah, it is called OpenNest. Okay, so if you have installed that plugin, then you get this group of components. And somehow he decided to put this into the category of parameters instead of creating a new category of itself. I don't know why. I don't think this is reasonable, but somehow this is what he did. Okay. So after you install it, you find your original parameters tab. You get one more panel, which is called OpenNest. Okay, and I think here in this example, it uses a row and pack object. Okay, this pack object component is helpful when you want to create like your laser cutting drawing. So you have to arrange all the component in a very efficient way so that you don't waste material. Okay? Usually we need to do this manually, so you have to move these things around and try to find the most compact way to do the laser cutting or the CNC. Okay? And somehow this pack object, try to arrange it. Okay, maybe not the optimal. You can still improve it, but at least it does a lot of work by making sure the bounding box of each component and try to arrange them in a good way. Okay, so it is helpful when you want to do digital fabrication. Okay, let's start with this Platonic. Where is it? Where I don't see it. Wow, so small. Okay. Okay, again, a geodesic sphere. This is 0, so it's from icosahedra. You know what is icosahedra, right? Yeah? Okay. Dodecahedron? 12-sided polyhedron, 12面体. Okay. R, the radius, level. No, this is the base plane, okay? And level 2, okay? So this is a mesh with 320 faces. So every triangle of the icosahedron is divided into 16 triangles. Okay, so there are triangles, but we want to get the dual of it. So they become hexagon and pentagons. And there are 12 pentagons. Okay, and then we want to planarize all the pentagons. Oh, no, pentagon. We don't need to planarize pentagon. They are already planarized. They are planar anyway. But for the hexagons, we need to planarize all the hexagons. So somehow the lengths of the edges are modified for the purpose of planarization. And after they are successfully planarized, then you can make them as filled surfaces. How come they don't fill it for me? I think the rendering engine somehow is ill. Okay, so it doesn't fill it, but I'm sure that they are created because here, after this boundary component, they become trim surfaces, right? And the condition that this boundary component will work is that all the input polylines are planar. Okay, so here I'm sure that this planarization works. Otherwise, you cannot generate these curved surfaces. Why? Why it doesn't create surfaces? Let me try this. Somehow it is here. How about the top view? Again, right view. Again. Let me try this. Let me create a new drawing. Still don't work. Doesn't work. Anyway, but I think if I quit Rhino and start it over again, it can be fixed. Okay, but anyway, we just leave it like that. So you get the planarized panels. Okay. Dual, and then with this point, find a plane. We cut the mesh, so you just want the semi-sphere, and make the mesh of it. Here is the data dam, okay. Then if you, I think you can double click it, no? Make a polyline of it, yeah. From polyline, make the mesh, okay. Find the naked vertices, because we want to, okay. These are the naked vertices, which is as the bottom line, bottom boundary of it. No, sorry, not like that. Okay, because they are separated, okay, they are not jointed, okay, so all the vertices, actually, they are all naked. And then you take one of them, just one of the vertices for every pentagon or hexagons. Why? Because now we want to arrange them on the plane, on the XY plane. This is to create a sharp drawing. And we need a base point for every pentagon and hexagon. So we just choose one vertex of them. And then we unroll the entire semisphere. This is the semisphere, okay? And we want to align, we want to put all these panels on the plane. We use this unroll. You can input mesh or breadth. Okay, for this component is from this, you see, this is from OpenNest. Okay, and curve, okay, you can also arrange curve, because for laser cutting, sometimes we need to cut curves, open curves, not necessarily enclosed surfaces. Point, this is the base point. You can have texts. You need to put some marks on it so that you know how to assemble them. And then you have text points. You need to arrange this point on the right adequate location so that you can reference them to the shapes. And these are the output. Okay, after these meshes are aligned, are transformed to the XY plane, and they are overlapping each other, it becomes like this. And these are the points, the base point, and these are the shapes. Okay, and then you can use this shape and the base point to pack them into a compact configuration. Okay, and you see you have columns and rows, right? And you see they try to arrange them in a compact way because it will check the width of each panel, and they try to compact them, right? Because like this one is so small, then it is the space is squeezed, and of course you can control the X, I think. You define the gap between each shape, and you can make it smaller. Can I make it 0? Yeah, if you make it 0, then you see they are squeezed. The space in between is squeezed. When these two edges are parallel, then they become one edge. When they are not parallel, then they become very close or even intersect. Oh, not intersect, but very close. Yeah, because this point and this point, they have the same x coordinate. Okay? So this is a good function so that you can somehow arrange all these figures in a compact way. And you can decide how many for one row, okay? And it depending on the total number of shapes that you want to cut, then, okay, and then you know the size of the material, the shape of the material, and then you find a way to best configure everything. Okay, so this pack and a row is kind of useful. Okay, and then yeah, blah blah blah. Okay. This is for joining them. So offset. In this case, then we should then to pack it with 0 distance. Okay. Because they offset it. Okay. Maybe for joining the two sides, and with this point, maybe you can drill holes in it, and then you fix the two panels using the holes or whatever. Okay. Okay, this is one example. This one, I don't know why. Maybe something is missing because there are some error mistakes. This one is very interesting. I don't know why they disable all of them, but I think we can start. There's another one. This one is also disabled. Why is that? Also disabled? Okay, this one. Here we have some surfaces joined together, become a bread. Okay, some surfaces join, and then we get one bread. Okay, this one, we have encountered it before, right? It tried to reorganize all these breadths. Okay, so that when it is trying to do division, it fits better with each other. So now we have this division. Make it a mesh. Actually, I mean, this one doesn't do anything. Just use this as a placeholder to put this mesh. Okay. Now this is Kangaroo goals. Okay. First, we want to show the mesh. Deconstruct the mesh so we get the vertices for sphere collision. We don't want these vertices in the transformation or in the simulation. We don't want the vertices to collide, to be too close to each other, and the distance is 10. Okay, the radius 5, so the distance is 10. Okay, and then we want to apply a load, a force upward, 0, 0, 1, so it is going upwards, and then the weighting of the load is 26. Okay, and all the mesh edges, we want to maintain the length, okay, with the strength 100. And the mesh edge, the naked edge, the outer boundary of, okay, we want to find the points. If the points are close to this line, they want to anchor them. So you can imagine that the structure will be anchored at points on these 4 short lines. And then we put everything together. Here, this technique is very useful and interesting. Okay, before I didn't know that we can use it this way, but this is very helpful. You don't flatten all the goal object. Instead, you use this NGon to create a tree structure, and you maintain the tree structure and send it to the input of the solver. Okay, now it is the simulation. You get this structure. It is simulating the load. So this is kind of a structurally very efficient shape. Okay, it's nearly catenary shape. Okay, so if we consider only the load from top, then this structure is nearly pure compression, okay, without tension and moment, and it is very efficient for masonry structures. Okay, so you get it. And why we preserve the tree structure of this goal object? Because if we preserve the tree structure, then you get the same tree structure for your output. In this output, you get everything, right? Lines, maybe surfaces, point, line, and mesh. And here, we want to get only the mesh. Okay, so now afterwards, you get the output and you explode the tree structure, and you are sure that mesh is at the first output of it. Because when you NGon all the goal objects, you put the mesh at the top. Okay, so you know exactly from which branch of the output what you can get from each branch. So you get the mesh, which is this one, triangulate it. Okay, triangulate it. You find a dual because we want to have hexagons and pentagons. And then here, this one split is also not so easy to understand, but somehow it tried to control the size of the division. Okay, the algorithm, I'm not so sure about the algorithm, but you see the dual here. Here you see a very large panel, right? And this is not so good for construction, so we split it based on the same configuration or the same pattern, but somehow we can reduce the size of it. Reduce the size of it. Okay? When it's very large, then you get large panels, but when it is small, it tries to reduce the sizes of all these panels. Okay, and you derive the mesh out of it. Okay, and this iteration is the number of steps that you want to have. Of course, with more steps, then maybe the computation is fine, then you get better result, but then it takes more time to do the computation. Because this shape is so simple, so it doesn't matter, okay? But when you are handling a very large and complicated structure, maybe you don't want to have this iteration too large, or you need to have very fast machine. And this is the smooth kind of parameter to control the smoothness. Okay, not necessarily the surface, but also the divisions. Okay, I'm not quite sure what does it means. Okay, cut large polygons. Yeah, this is the example using NGons and then using Kangaroo to doing the simulation. And actually, another thing you can do is to try to planetize all these panels. Here, it doesn't do that, but we can do that. If you want to use material like plywood or even stones to create this shape. Or actually, I think ETH, they have a structure using stone, panelized stone, and build a structure, tension-free structure in Venice. This exhibition, very famous exhibition, every 2 years in always in Venice, right? Victor? Yeah. You know that event, right? Yeah. Every 2 years, always in Venice. Okay. And this very famous structure designed and created by Professor Philip Bloch from ETH. Okay. So I'm not quite sure if we can do something like that following this process. I'm not quite sure. We still have to check it. But using Kangaroo to simulate, to find the form, maybe the shape is nearly tension-free. Okay. Okay, let's call it for the day. And next Wednesday, I'm expecting to see your presentation and your installation. Okay, good. And I will add more exercise and video. Oh, let me stop this here.